Welcome back. So let's continue the discussion on turbulent combustion. So we are looking at the different governing equations, and the one which we are doing right now, the discussion is the conservation equation of the total energy. So this is how the total energy equation would look like when you look at the control volume, and the different terminologies we have discussed. So here there are two components, one is this component, another is this component. Now we have already looked at this Q. There are three components to that. One could be due to conduction, then interdiffusion, and finally the Dufour effect. So this is due to heat conduction heat flux, this is due to species diffusion, and this is due to gradient in species concentration. Then we looked at the non-dimensional number and all this. So now we look at the source term of the total energy, that is WET. There would be stress component plus there would be body force, and there would be component if there is any other sources. So the stress component one can represent as del dot sigma dot V, which is the work by stresses. Body force component one can represent like rho summation of I1 to n yi Fi dot B plus Vi. This is the work done due to body forces, and the other sources one can keep it Q. This could be source or sink term. Let us say if you have radiation effect and some other effects which would provide some source term, so that can be taken into consideration under term. So one has to note there is no source due to heat release by reaction. So this is one can note that, and that is a because that is a transformation between two forms of energy, both contained in internal energy, which is in chemical and thermal. So if you include everything together, the equation would look like this is my unsteady term, convection term, this is the flux due to conduction, interdiffusion, Dufour, source term like this, and which will can be written like this also. So now this is we need another equation for temperature to solve this. So we invoke the equation of state. So one is the thermodynamical equation of state, where P would be rho by W bar RU T. So that will relate pressure, molar density and temperature, and W bar is mixture molecular weight, which would be Xi Wi. Apart from this, we need caloric equation of state, which will give us H equals to delta HF naught plus the temperature difference. Here H I would be delta H naught I plus T naught to T Cpi dt prime. So this is an enthalpy of species I, and this is essentially the enthalpy of mixture, where H one can write in terms of Et minus half plus P by rho. So once we write this from here, we can actually estimate the temperature from this. Now, more how this calorie equation of state. So, these are the multi-component mixture, which is an example of natural gas where by and large CH4 is there, then other components are there. So, this actually relates the enthalpy and temperature for a given pressure and composition. So, this is your individual species enthalpy, and from there this is my mixture enthalpy. Now, one can also get that one by getting H equals to summation of yi hi. So, that is also can be used, where delta Hf naught is the summation of all the species and Cp is like that. So, these set of equations are also valid, and for multi-component mixture one can use that. Now, if you look at the specific heat and other possible energy variables and have an idea how that actually varies. So, you look at here the mass heat capacity, this is the scaled molar heat capacity, this is varying with temperature. So, this picture is adapted from the book from the Ponshaw and Bhenante. This is for different mixture, you can see how that varies over a period temperature. Same thing here. So, if you put all these different form of energy, then we can see the relationship between energy and the enthalpy. So, the sensible energy one can write ES, which is S stands for the sensible energy, which is an integration of Cv dt minus, and sensible enthalpy would be only Cp dt. So, that this component would the integration of Cp over a range of temperature would provide the sensible enthalpy. Now, once we add sensible plus chemical, so here the energy component, that ES is coming from sensible, and then this is the component due to the chemical energy, that individual change in enthalpy for individual species and the sum over all the species. So, and in terms of enthalpy, there would be component coming from the sensible one, and this is the component due to chemical one. So, the total chemical would be E plus half uy square, and Ht would be H this, and non-chemical sensible plus kinetic energy, this is sensible plus kinetic energy. So, this is a correlation that one can see. Now, we can write the transport equation in terms of internal energy. So, this is the conservation equation, where left hand side is the total derivative of that, and we have the flux, gradient of the flux, and the body forces term or the source term. So, this is essentially our source term. Now, this is stress component, body force component, and other component. Now, kinetic energy, one can write that total kinetic energy is the derivative of the kinetic energy V dot source term and this. So, one can find out the internal energy equals to total energy minus kinetic energy. So, this is what we get in the left hand side, ddt of E, and right hand side we get this term and remain this term and the other term. So, one can go for equation of total energy to equation of internal energy. So, one can start from the momentum equation, which will give you the Navier-Stokes equation or these things, So, multiply this one with the V or the scalar product of that. So, this equation we take in scalar product and that will give me this. Now, here we can rewrite the left hand side term like this, right hand side term like this, and the other term in this fashion. So, look at the source term for that. We have body force, which is summation of yi dot v plus vi. So, one can write that body force minus rho summation of I to n yi fi dot v equals to rho summation of n yi fi dot capital Vi. So, one can write that. So, the source due to product and the force diffusion velocity. Now, the stress sigma dot V, which is V dot sigma plus sigma V, where one can write the stress minus V dot del dot sigma equals to sigma bar. So, that is an tensor product. So, this is an source due to stress and other would be Q. So, this is source due to other terms. Now, one can look at the change in the energy, internal energy due to stress. So, the sigma is written as minus Pi plus tau, where tau is given as minus 2/3 mu del dot Vi plus mu del V plus del V transport, like that. So, the tensor product of that would be sigma flow plus sigma viscous. So, this is an important correlation, and sigma flow for this is minus Pi dot del V, which is minus P del dot V, which is a flow work. Then this viscous equals to tau double dot del V, which is a, one can think about viscous dissipation, and then we can say minus 2/3 mu del dot V plus mu del V transport. So, this is double product with del V plus transport. So, this is my viscous term. Transport equation, if I look at it finally for the internal energy, this is the term left hand side total derivative, heat flux, stress and other term. If I just rearrange that, so this will get viscous, this term, other source term, pressure stress, and this, but the viscous term is representative like that. Now, similarly, one can derive the transport equation for enthalpy. So, how do you do that? We actually write this equation, which is rho ddt of H minus P by rho equals to rho dH by dt minus dP by dt plus P by rho d rho by dt. So, this is essentially our continuity equation. So, one can write rho dE by dt, dH by dt, dP by dt, P del dot V. So if we rearrange that, my dH by dt equals to rho mine plus P by dt plus P del dot V. So now we can use that d small e by dt equals to this equation which you already obtained in the expression where we get the dH by dt. So if you use this one, this expression back in here, then we get rho dH by dt minus this heat flux, viscous dissipation, other term, then this term will remain as it is, and we have the source term coming in. So now we can see the how we evaluate the temperature from the enthalpy equation. We have individual species enthalpy, then from there if we take the derivative of that, this will give me d Hi by dt equals to Cpi dt by dt. Now change of mixture enthalpy by sum over all the species. So dH by dt, if we take the sum, so this will be sum over ddt of y by h. If we take the derivative the first term, so this will be the total derivative of mass fraction multiplied by individual enthalpy, mass fraction taking individual derivative of the enthalpy. So dH by dt will come like this term remain as it is, and here we change this particular term, we replace with this, so that we get yi Cpi dT of dt. So this is nothing but the algebra. Now we write dH by dt, we keep this term as it is and this term. So here if we look at rho Cp T ddt by dt, rho dH by dt minus, so if we take this sum, this essentially the sum over this all these things, this will get me Cp, that is the mixture Cp already which have obtained. So that derivative of temperature is this minus this guy. So now you can use the equation of y and h to obtain the temperature equation. So that will give me rho Cp dt by dt. So this one is coming from my these things, this guy will contribute to that, and this is the one which will come from there. So if one look at this particular expression, there are so many terms which are involved in this process. Now we can see when the Dufour effect is negligible, our energy flux can be written delta T plus rho summation over all the species Hi, Yi, Vi. So then one can write minus del dot U plus summation over I tends to 1 Hi del dot rho Vi Yi equals to del dot delta T plus rho Yi Vi dot Hi. Now this particular term, and also we use del dot Hi equals to Cpi del T, then the temperature equation become rho Cp dt by dt equals to del dot lambda del T plus Q phi dp by dt summation y2n rho yi fi dot vi minus rho del T dot product with, so this one can be third bracket, so this is dot product with VAI, YI and CPI minus this is what it is. Now if you look at the book of Co, the temperature equation would be slightly different because some assumption on specific heat are made. So that's pretty much give you an idea different form that the energy equation can be presented. One is total energy, internal energy or enthalpy or temperature. Now if I just sort of put the things back together, what is important here to look at is the basic governing equation that one has to have is continuity, this would be like this, then momentum, then you have individual mass fraction of species where this is the chemical source term and that will tell you whether the species production is there or destruction is there, so that will come from that. Then we have specific enthalpy which is a total of chemical plus thermal, so this is heat flux term, this is heat source and this is any other source term. So that's pretty much taking into account these are my basic governing equation that required for my reacting system. Now top of that what you need when it is turbulent, you need the turbulent equation. Turbulent equation. If it is Rans based equation, then you require Rans based equations, Rans based turbulence model, or if it is LES, then you require LES based modeling approach, and that we see once we move along with our discussion. So one can do some simplifications here. Let us say we can categorize like what are the feature and the cases we can simplify accordingly. Let us say if it is time dependent or dependence, then one can make steady or unsteady. So these are the possibilities. Time dependence, then you can have spatial dependence which will give you whether it's 1D, 2D or 3D. Then depending on rate of reaction, so you could have chemical equilibrium or effect of finite rate chemistry. Then you can have kinetic scheme which could be simplified or rather reduced or detailed. Then you can have diffusion which will be either Fick's law or multi-component transport. And finally, if you have radiative heat loss, this can be either neglected most of the cases or included. So you can have certain features, and accordingly you can simplify the cases. So, that is why it allows you to do some sort of an possible these things. Now, this is an image of an 2D reacting mixing layer. This is an temperature contour. You can see the reaction zone and all these things due to the vortexes, and these are the zoomed in pattern of that. Here the kinetics is simplified because we have fuel plus oxidizer to product, and the possible simplification for the temperature is that we do not have the effect of Q, viscous dissipation, pressure gradient, these. So, it is a simplified temperature equation which is one can solve. This just give you an idea that how you can simplify. Now, we looked at the set of Gaon equations. Now, straightway, since our discussion is primarily on turbulent combustion, we start looking at the system when we go to Rans's based approach. That means, when you go to Rans's based approach, this would be averaged equation. So, the averaged equation, the balance equation, the continuity will look like this. These are Reynolds averaging or the Reynolds averaged equation. Navier-Stokes will become like that, and you get an shear stress term which will also contribute to the eddy viscosity. Species mass fraction equation also will have a diffusion flux, and this is an average source term, and specific enthalpy will also have the heat flux and the other source term. Now, this would be mass fractions would be an sort of an scalar vector. Now, there are average of these products. These are like rho uj, this would be rho plus rho uj plus uj prime. So, rho uj prime would be rho bar uj bar, rho bar uj prime plus rho prime uj bar, rho prime uj prime. So, one can write this is rho bar uj bar plus rho prime uj prime of this. So, that is using the averaging property for Rans's based framework. Now, we can write also the other term. This would be rho bar plus rho ui plus ui prime uj plus uj prime over this. So, this would become like rho bar ui uj plus rho bar ui prime uj prime plus ui rho prime uj prime plus uj rho prime ua prime plus rho prime ua prime uj prime. Now, the terms which containing the density fluctuations do not appear in the alternative approach. So, that is why if we use the density average, density weighted average, that would not appear. So, that is how we will look at it, how you can eliminate those terms using fluctuations of the density fluctuation. So, we will stop here today, and we will continue the discussion in the next lecture.